Hi, everyone. My name is Connor Hewson, and this summer I worked with Dr. Philip Sprengel on the linear and nonlinear analysis of the Cherenkov traveling wave amplifier. So first, a quick overview. Compact, high-power amplifiers operating in the gigahertz regime have several applications ranging from RF communications to electronic disruption. So we analyzed and numerically simulated a Cherenkov traveling wave amplifier to achieve high power on the order of a gigawatt over a very wide frequency range from 1 to 3 gigahertz. So our configuration consists of an annular relativistic electron beam and a cylindrical waveguide with a corrugated interconductor. And this geometry is unique for giving us this broadband, wide frequency range amplification. So this is an example of a corrugated waveguide. So we see here that we have a conductor tube that the radiation propagates down, and we also have corrugations along it. Our particular design is slightly different in the fact that it has an inner conductor as well, so it's not hollow, and the corrugation is along the inner conductor. We have an annular electron beam that propagates down, and we have a flat outer conductor. And we also have a profile view here that shows the corrugations. They're periodic in nature along Z, and we have our electron beam propagating. So to continue the overview, this geometry supports a subluminal hybrid TM/TEM mode, and subluminal just means that the phase velocity is below the speed of light, and this is able to couple to the electron beam over a very wide frequency range. So this coupling occurs between the electron beam and the input signal, and we get high gain amplification. In the linear regime, we were able to find that the power E folding length, which is just the length for the power to increase by a factor of E, we found that these lengths were less than 1 meter for beam currents of around 5 kiloamps, and with energies on the order of 1 mega electron volt. And we were also defined in the nonlinear regime conversion efficiencies, which is the ratio of the output wave energy or power to the input electron beam power, were over 20%. So this is another view of the configuration. To solve for the dispersion relation in the waveguide, this was the form that our fields took. One thing that you need to note here is that to be able to satisfy these periodic boundary conditions on the lower inner conductor, we had to represent our wave number in terms of spatial harmonics, where the wave number here is indexed by an integer and the period of the corrugations. Yeah, we needed to do that to satisfy all these boundary conditions. So inside the actual corrugation cavities themselves, the fields took on the following form. And the last thing we would do is we matched the boundary conditions at the outer conductor across the electron beam and across x equals 0 at the lower conductor. And that would give us a dispersion relation, which was just the relationship between the frequency and the wave number as a function of the geometry and the beam parameters. So this is the a dispersion diagram of the type of dispersion relation we got. You see here that the dispersion relation of the beam mode and the hybrid mode overlap over a very wide frequency range, giving us this coupling and amplification over the wide frequency range. This is in contrast to more of a standard TM mode that we would see where the phase velocity is greater than the speed of light. Here we do not get the coupling over a wide frequency range. So the corrugated geometry is unique in its capabilities to give us a broadband amplifier. So this is the addition of the sheet electron beam modified the dispersion relation and resulted in amplification. This is the following dispersion relation we get. It's very complicated, but it can be grouped into 3 different terms. The first one is the beam mode. This is the beam's dispersion relation. This is the hybrid modes, hybrid corrugated waveguide dispersion relation. And then these are equal to a coupling term. And this coupling term is just a function of frequency, geometry, and beam parameters. So we were able to take this and solve for the linear growth rate and wave number shift of the radiation. And this is contained in this term called delta K. You'll notice that it's a cubic equation, so it has 3 distinct solutions. One of those solutions exponentially decays in distance, one of those is constant in distance, and one is exponentially growing in distance. And of course, since we're making an amplifier, we're interested in the one that is exponentially growing in distance. And for that particular mode, the spatial growth rate is given by the negative imaginary part of delta K, and the wave number shift is given by the real part of delta K. So we find that the power e-folding distance, which is given by 1/2 times the spatial growth rate mentioned, is under 1 meter given these parameters with a beam current around 5 kiloamps and beam energy at 1.28 mega electron volts, which is about a little over 90% the speed of light. So during this interaction, what's physically happening is the electrons are trapped by the subluminal wave. And during this process, kinetic energy goes from the electron beam into the wave, leading to amplification of the wave. So to calculate the conversion efficiency, we take, as mentioned, the ratio of the output power to the input power of the beam, which can also be written as the change in kinetic energy of the beam divided by its initial kinetic energy. So to estimate this conversion efficiency, we say the trapped electrons have a velocity equal to the phase velocity of this trapping wave. And then we are able to find a conversion efficiency that is written in terms of this wave number shift that I brought up earlier. And by plotting this, we see clearly here that we get conversion efficiencies above 20% for frequencies between 1 and 3 gigahertz. For us, that indicates that we can obtain powers on the order of 8 gigawatt with these conversion efficiencies. So in summary, the Cherenkov traveling wave amplifier is based on this interaction between the subluminal TM/TEM mode and a relativistic electron beam mode. This interaction allows for amplification over a very wide frequency range in the gigahertz regime from 1 to 3 gigahertz. And we get output power levels on the order of 1 gigawatt with efficiencies greater than 20%. In addition, we could pre-modulate the beam and also introduce a tapered waveguide such that we could actually further improve the conversion efficiency and get even greater output powers. All right, thank you.